Okay, so let's add attention to our seq2seq model for a very simple example that we can cook along the way. And we want to see how it allowed the decoder to have a differentiable access to all of these encoder states. Okay, so for this, I'm going to assume a very simple minimal reverse task, meaning that, let's say we have an input of integers, let's say x1, x2, dot, dot, until xt. And then we want to learn how to reverse this. So given an input like that, we want the neural network to learn the reversal task. Okay, so the reverse will be t minus 1, dot, 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 x1 until end of the sentence. Okay, so this is basically like the contract that we want to have the model solve. So why reverse? Because, well, the first output depends on the last input, which requires a long range dependency. Somehow it stresses the fixed size bottleneck and showcases how attention removes this bottleneck. Okay. So just to do a recap, we have data pooling using attention. Let's say an alpha, going to get alpha from somewhere. Okay, so let's do a recap on uh, the formulation of attention. We are going to do the simplest possible form of that. And then maybe along the way, we can tweak it. As we learn data pooling, that learns its similarity between the data. Here, the query or the decoder state and the keys or encoder state. And this way, after the softmax, we get these weightings. And using this weighting, we have this weighted sum of the values. And then we use alpha for this weighted sum that gives us the context that we will use for the next decoder state. So remember that we call this C in our formulation. And to compute A, we use the scale.product. Recall that we also had a rotation on Q and K using WQ and WK. Let's import some modules and then we'll set up this problem that we discussed here. Okay, so let's make a simple example or data. Let's say of 20 possible different integers. So we are looking at vocabulary size of 20. Let's give a pad token of 0. So this is the token for the paddings. Since this is a seq2seq, we will have padding in the cases that the number of input sequence is less than the maximum sequence size. Okay, so let's have a start of sequence token. Let's just give it a vocab size +2, +1 here, which basically we make it 21, and an end of sequence token +2. We have a max length, basically what I mean, the total vocab size, which here will be vocab size +3. And note that yes, we are working with this integers, but we could easily add text, for example, or words that we wanted to do the reversal. But here we don't want to deal with the text processing, tokenization, vocabulary building. We just basically generate these random sequences, and NLP aspect is not of our interest for now. Okay, so this is the dimensions of the each RNN cell that we'll need together for the encoder and decoder. So we are looking at a 32-dimensional hidden state or embedding that will be carried over or in this RNN cells. And let's use GRU cells. And we are making 1,500 number of samples. or training pairs, and the batch size 64, number of epochs 80, and let's assume two different cases. Let's one time we can train this architecture with a short sequence of size 5, and then one time with a longer sequence of size 20, which is much more difficult. So these are the two possible sequences that we want the model to handle. Let's make a dataset class that makes this example pairs with shape handling and tokenization that we discussed. So this here is the class. And for example, if you want to sample the short sequences or long sequences, we can do it using this. So now we have the data set for the short and long sequences. For example, if you want to look at the first example in short sequence, here is the example. So we take in this value. This is token 21, which is the start of sequence, and then the reversal. So if you assume that we have this decoder output. Okay, so let's make the vanilla encoder something that you already know. So I will be fast. I just include the code. So here is our encoder, which is a GRU, and we know how it works. So let's write the decoder, and here is the decoder, same GRU cell RNN. Okay, so during the training, of course, we are using teacher forcing, meaning that we are using the ground truth token instead of the model's prediction, but that's not possible during the inference. So that ground truth token, we call it gold token. Just remember if you heard that. Okay, so, and remember that here the decoder state takes in the entire sequence. This makes some optimization behind the scene. It's not really parallelization. Basically, it's much better than a for loop. The real parallelization will happen later when we go to self-attention and transformers. So that's the decoder. Now let's write a seq2seq class. So class vanilla seq2seq, which has the encoder and decoder, and this is the forward methods. Okay, great. So with that, let's implement the seq2seq with attention. So first we need to write the attention mechanism, scale that product attention. Okay, so for that, let's write the class attention mechanism. So we compute the scores, and then we compute the softmax, weights, and then we do the kernel regression for the context. In this case of RNN, V happens to be the same as the hidden state. Okay, so here I note that I used an implicit WV. It's not really necessary here. Okay, so with that, the init. We need hidden dimension, and let's just simplify the syntax. I know that I told you to do the good practice, but here don't want a screen splash. I want you to pay attention to what matters at this point. So we need WQ, which is a linear. So remember, this is just a rotation. It's not an affine transformation. And another linear for WK, and same deal. Like I said, I don't really need this, so let's just forget that for now. We are opting for simplicity. We need the scaling, which is basically this variance stabilization that we discussed. So we need a float output of NP SQRT hidden dimension. So this is, like I said, that 1 over square root of dk. Good, so let's write the forward method. We have the query Q and the keys. And with that, remember a query is the current decoder state of size batch, and hidden keys is, of course, the sequence length. And we return the context of size batch and hidden. And then at the end, attention weights, which is the size of batch and sequence, input sequence length. So we are returning not just this, we are also returning the context. So what I mean is this. So the context, which is the kernel regression, and then we are doing it for the number of encoder states. Okay, let's call it attention weights. Here we have that. Just to be in line with what I said at the beginning, I'm going to just call it Q and K, but this is really the uppercase Q and K in the notes. Okay, so we have a 2D tensor Q and a 3D tensor K. And now we want to compute the matrix multiplication, but we want to use batch matrix multiplication, which requires tensors of the same dimension. So with that, I'm going to just add another dimension here in a safe way. We know how to do it using unsqueeze. So let's do it, and this will return this. And then we can do batch matrix multiplication using torch BMM. So torch BMM will give us the scores. So this is scores. And this is basically what we were wishing for, the inner product in the most efficient way that capitalize all of these resources that we have, right? Okay, so how to get the attention weights? We basically do the softmax. We are doing it from the functional, from the scores, and we do the softmax over dimension 2. So remember the dimension of t. Maybe it's good to explain why here. So here in this scores, when we do the batch matmul, so we basically do multiplication of tensor of size this with a tensor of size this, which returns tensor of size B1 and T. So this will return tensor of size this. This is another matmul of sizing batch T and H, which returns H1, H, right? Okay, great. So that's the context, and we can basically return the squeeze version of them. So remember that we only unsqueeze for the batch multiplication. That's the attention mechanism. We're done with that. We just need to write the encoder. So like I said, I need an encoder that returns all of these hidden states. Let's call it attention encoder, even though there's no attention really within this. We just return everything for the attention decoder. Okay, so it's basically the same thing, just returns all of the hidden states. Okay, I added some commentation for you. Okay, now let's write attention decoder. Here in this class, we want to basically do a one-step decoder attention. I mean, at each step, if you remember indexed by T, we want to form a query from the current decoder hidden state, which is HT-1, and we want to compute attention weights over encoder outputs. And then using that attention weights, we concatenate the computed context T and the embedding T, we give it to the GRU cell and predict the next token distribution from this output T and context T. So I will write this down. So this is basically what we are trying to do. And with that, let's write the init. We need the hidden dimension, self embedding. Remember, we have this total vocabulary size, we have the hidden dimensions, and then let's write the self attention. Which is an attention mechanism size, a hidden dim. Then we have these GRU cells. Okay, looks good. And then we have the FC that requires an input of size hidden dimension multiplied by 2. Now let's write the forward. Okay, what we have X hidden encoder outputs. Great. And what's X is basically the current input token. Hidden is the previous decoder state. And the encoder outputs is basically all of these encoder states. And we want to return the logits, the hidden, everything at time t, logits, hidden, and attention weights. Okay, so like I said, we need the embedding. We are using the current decoder state as our query, B and H. Remember that still we need to do the concatenation, and of course we have to take care of that. Okay, so that's the query, and now we have the query, we have the embedding, we can pass it to our attention. Okay, we have it here. Great. So query encoder outputs, BHBT, that's correct. Let's just simplify. This is the context and this attention weight. Now we want to concatenate the token embedding with this context, right? And that will be the GRU input. Okay, we have it here. cat embedding. Oh, now that we have this RNN input, we can advance one GRU step. So we have to concatenate the output and the context, and then send them to the feed-forward predictor. So first, let's call this the prediction input, which is this output, and here you see an ask quiz to make sure they have the same dimensions, and then we pass this to the feed forward or FC, the fully connected prediction head that predicts the token. Okay, and the output is the logits at time t. And then we are returning the hidden and attention weight. So we have everything to write our class, the class of attention seq2seq. What we have here, great. And then just like before, a def encode, decode. Okay, we have that too. Okay, so let's do the training. Remember that training is with teacher forcing. What I mean is we feed the true previous token to the decoder during the training, but of course we don't have that at inference time. The loss will be a token level cross entropy over the entire T+1 decoder steps, of course, including the end of sequence token. So we have to make sure in the cross entropy loss, we will ignore the padding tokens. That's the only thing that we should take care of. Okay, so with that, let's write the train model. So we take in model, let's pass the learning rate too. So with that, just to write what I mean here about the train with the teacher forcing. Okay, so now the optimizer. Let's do that. Okay, so takes in model parameters, learning rate. Okay, criteria and cross entropy. Of course, we got this as a suggestion. That's great. Before train, just make sure you're sending it to device. That's that. Loader is the data loader, and that takes in the data set. We have the batch size and everything, so let's just use that. Shuffle through. We don't need this. Okay, for epochs, let's before writing this, just make sure we have empty list for recording the accuracies and also time. Let's do time. Okay, so for epoch in range, we need the epoch loss to start epoch loss and correct and total. We need to initiate this values our recording. We want to initiate this for keeping the tally. Okay, so for source, target input, target output in loader, we have source, that, send to device, and then optimizer, no grad, zero grad. So let's, because I want to run this in two different ways of attention and no attention, let's define an is attention instance here. Let's do it here. So is attention is an instance The model is attention seek2seq. If is attention, basically run the modeling code once per batch. And then we want to do step-by-step decoding. And to do that, let's accept this and simplify. Then creds, which we need to populate, like I said, in a step-by-step decoding. So for T in range, this requires a teacher forcing a token. So I have to first get the token to use it instead of this, which happens during the inference, of course. But here for the training, we have to do teacher forcing. Okay, so that's that. Good. And now else the vanilla seq2seq, remember? So in this case, hidden encode source. Here we are just leaving it to PyTorch GRU that does everything. It basically decodes the forced sequence in parallel. So it does itself. We don't need to do anything. Did I forget something? So for T that's the pred. Oh, we have to output something here, right? So output cat preds dim1, which will be f size b, the decoded sequence, and v. Now going back here, the output here is the output of the decoder. And let's accept this, and that's that. And this is of the same size. We're done with that part. Now we have to compute the loss. We got the suggestion and okay, view output shape, target output. So this is basically cross entropy over all of these time steps. We flatten batches and times, and we do the loss backward, and then optimizer. We can, for example, clip the gradient here before the step, right? Let's record the epoch loss, and let's look at the token accuracy. So epoch loss, let's first compute the predicted token, which is a size batch and the decoder sequence. And let's mask the paths, and let's compute the correct predictions. We may have an error here, but let's accept this for now. And then, so of course, if total is not 0, we should be careful here. So then we can append that. I had the epoch loss, so let's just record average loss too. That's that. We just need to return the accuracies. Let's actually add some verbose to just show the epoch losses and the token accuracy when it finishes, the timing of that, and then we will return the accuracy. So I'm gonna add that. Let's run this. In the meantime, we can write a function for evaluation. Basically, we want to evaluate the sequence with a greedy decoding, meaning that we don't have any teacher forcing anymore, right? We require the exact match of the entire T+1 length sequence, even including the end of sequence, right? I assume you know this function because you wrote this in the assignment. Then I will write evaluation and some visualization code. I also included a plotting that basically shows the comparison of this evaluation. What else? We can also write a function that visualizes the attention. Why this is interesting? Because I want to show that how attention manages to look way back in the past to align the first decoder state to the first encoder state. So first, let's look at this. We see that attention works perfect in the case of short sequences. I had some errors in how I'm recording the token accuracy, so I have to revisit that. But the sequence accuracy we see it here, we are not doing well in the vanilla for long sequences because of that issue, the bottleneck issue that is the worst in this case. It has to look back 20 states back to be able to understand the reversal. We don't have that issue with attention. Here you see that I made an error here. I have to go back and fix it. But for now, let's rely on this. And I want to also look at these attention patterns, and let's do it. So basically one example and we visualize the attention weights. Okay. I will share the code with you. This is just a thing. We just need to, if we run the visualize attention weights, it will return a fig. So fig visual. Okay, so if we do it, basically the input sequence, output sequence. So input is 24, 19, 4, 7 until 16, and the output is 16, 5. And looked at the first output is looking at the first input. So this is basically a long range attention that we are talking about. Basically, it's the max out length, right? It's instead of that diagonal here, we have the other diagonal. We will look at the purely attention-based neural networks. We drop even the RNN and we use self-attention to do the encoding.